This lesson deals with differential and common mode signals. You can find these notes in the ECE302 ebook in Chapter 6 starting on page 1. Suppose I have a circuit that I can draw into two boxes where the circuit in these two boxes are identical. In other words, if you were to put a mirror here, the mirror would be showing you what this looks like from this angle, and that would be exactly the same as what's over here. Let's apply a voltage to one side of the box, and on the other side of the box, let's apply the same voltage and magnitude, but the opposite sign. And let's find the voltages on these common wires and the currents through these common wires due to these two sources. And way you could do that is if it's linear, we could do superposition. Setting this equal to 0, I would then solve for the voltages and the currents due to the left-hand source. And I'll indicate that as a superscript. Now set the left-hand source equal to 0 by making it a short circuit and apply the second voltage. And again, solve for these voltages and these currents. Because the circuit's linear, if you take all the voltages in your circuit and multiply them by a constant, it multiplies the voltage and the current by that same constant. In this case, the constant is a -1. The voltage on these wires are in the same position as the voltage on these wires because I'm just rotating this picture. So the voltage V1R is the same as this voltage except that it has the opposite sign. V1R is the same as minus V1L. The currents, the same thing will be true. By applying this, you change the value of the current's direction. But looking at the circuit this way is the same as looking at the circuit here with the directions reversed. Looking at it this way, you see the current flowing this way, but now that same direction, when you rotate it, would be going in this direction. This current is actually the negative of this current, but because my input was multiplied by -1, those two sign changes cancel each other. Voltages on the common wires have the same magnitude, but the opposite sign. And the currents have the same magnitude and the same sign. Let's add up the results. Add up the voltages at node 1, node 2, and so on. It's going to be the sum of the right and the left, but they're opposite signs, so it's going to sum to 0. All these common wires are sitting at 0 volts. Add up the currents, the same way, add up these two currents, but they have the same magnitude and the same angle, so they're going to be some value that's not 0, unless they're both 0. But here I've got a set of conditions on these wires where the voltages are all 0, and the currents are whatever they need to be. What circuit element has current but has no voltage? Well, it's a short circuit. We could replace these common wires on the original box with a short circuit and analyze this half circuit. And what you're going to get is a voltage inside this box or a current, and the same voltage or current on this side of the circuit would be the same amplitude but the opposite sign. In other words, a negative of it. Suppose we take the same two boxes but now apply a voltage to each side of the box that has the same amplitude and angle. Let's again find the voltages and currents due to these two sources. Again, I'll indicate this as V1 through V sub n and I1 through I sub n due to the left source. Do the next step of superposition by setting the left-hand side equal to 0 and apply a voltage. It's going to be the same magnitude and angle as the previous one, and we'll get a voltage and a current on these wires. When you look at this circuit and look at this circuit, there's simply a rotation of this to look like this. The circuit from this direction looks the same as the circuit from this direction. Common wires have the same voltage on them. V1R is the same as V1L through N. Current is going in this direction. Now when I flip this, that same current is pointing in the opposite direction. With the same amplitude, I'm going to multiply the previous results by a +1. I'm going to have the opposite direction of current here that I did over here. Again, looking at the circuit this way and looking at it this way, that same current is in the opposite direction. By adding up those, they're going to cancel each other. All the currents are going to sum to 0, but the voltages will be whatever they need to be. What circuit element has voltage but no current? That would be an open circuit. You could cut these common wires and analyze this box, find the voltage or a current, and that same voltage and current in this box would have the same amplitude and angle. So these are called common mode signals, and the previous ones were called differential mode signals. By cutting these circuits in half or by shorting the wires, we actually cut the work down dramatically. It also tells us a little bit about what's going on in the circuit relative to the differential signal and the common mode signal. This method of analysis is called Bartlett's bisection theorem, and it was proposed by Albert Bartlett in a paper in 1927 where he was studying symmetry in circuits. Suppose I have a circuit that has two terminals. I'll label one V1 and V2. Let me define the differential mode signal as the difference of the two. So I'm arbitrarily going to take V2 minus V1, and we'll stick with that notation throughout the course. Let me next define the common mode signal as the average of the two. In other words, add up V1 and V2 and divide by 2. I have two equations and two unknowns, V1 and V2, and I can solve for V1 and V2. So V2 is the common mode signal plus half the differential mode signal. And V1 is the common mode signal minus half the differential mode signal. Now, I didn't show the algebra here, but let's do a quick check on it. If I were to take V2 minus V1, I would have this minus this, that would cancel, and I would get this minus a minus this, so I'd get this twice. I get V sub d. That checks that I did the algebra correctly. Let's try this one here. If I were to add these two together, these two would cancel, and I would get twice V sub c divided by 2, and that's equal to V sub c. Even though I didn't show the algebra, it appears as if I did it correctly. I could characterize these two nodes in a circuit with an equation relating to the common and differential mode signals. I can make up an equivalent circuit for this in the following way. V2 is equal to V sub d over 2 plus V sub c, two voltage sources in series. And then for this equation, if you go from V1, I get minus V sub d over 2 plus V sub c. I can make up a circuit that can give me those particular voltages. This is just one model. It's called a T-equivalent circuit. It looks like the letter T on its side. If I were to apply this T-equivalent circuit to an amplifier, I would get an output voltage due to the differential mode signal and the common mode signal. These are going to be amplifiers, so this is going to be usually a gain greater than 1, but it doesn't have to be. We're going to call this the differential mode gain and this the common mode gain. Sometimes it's not convenient to use this T-equivalent circuit, but maybe the following. And that is just to put the equation for V2 as the sum of two voltage sources, and V1 is the difference of two voltage sources. In other words, V2 is equal to VID over 2 plus V sub IC, and V1 is minus VID over 2 plus V sub IC. And these are some definitions and properties of differential and common mode signals.